This presentation on hydraulic actuators, the third in a series of video training programs, provides a comprehensive introduction to hydraulics. I'm Paul Cook for Vickers. Let's consider the actuator, which you might think of as the business end of a hydraulic circuit. It provides the output motion and develops the force or torque the system requires to do the work. The job to be done and the speed, force, and torque requirements will determine the necessary size of the hydraulic actuator to be used. If we're dealing with applications where we have straight line or linear motion, we use a hydraulic cylinder. Applications requiring rotary motion use a hydraulic motor. Let's first take a look at hydraulic cylinders. They come in many varieties and sizes. This one is a single-acting cylinder or ram. Single-acting in that it's hydraulically powered in only one direction. It's returned either by its own weight or by some external force. One application might be a forklift truck, where we would hydraulically power the load up, but let the weight of the load, in other words gravity, move the cylinder down. Now, this illustration shows another single-acting cylinder, one that's known as a telescoping type. It's usually used where we need a very long extension, but must keep its installed or stored length in a much smaller area. For example, the cylinder like this might be used on a dump truck to raise up the container section. When the cylinder is returned by the weight of the big container, its length is telescoped down to fit into a minimum of space. Here we see the most common of all cylinders. It's a double-acting cylinder with a single rod. It's shown with the piston rod extending. Oil from the pump is directed to what's called the cap end of the cylinder. Oil from the rod side is at the same time being exhausted to tank, usually through a directional control valve. In the next picture, oil is directed to the rod side of the cylinder, pushing on the annular area around the rod and moving the load down. Oil from the cap end is now being returned to tank. Now, what about speed and force of the cylinder of this type? We can see here that we have a greater area on the cap end than we do on the rod side, simply because the rod takes up some of the space. We have more square inches of area to push on, which means since force is equal to pressure times area, that we're able to exert a greater force extending than when we're retracting. This will also affect their speed. As we can see, we have a larger space to fill here than we have here. Because the rod occupies some of that space, it's going to take longer to fill and extend the piston rod when we're directing oil into the cap end than it will to retract it when we direct oil into the rod side. If this were a 2-to-1 area ratio cylinder, meaning that we have twice as many square inches on this side as we have around the rod, it would take twice as long to extend as it would to retract. But it would provide twice as much force when extending. Now, let's turn to an illustration of another double-acting cylinder. This one has a rod extending out of each end. If both rods are the same size, we'll have equal forces and, of course, equal speeds in both directions, because the spaces around the rod would be the same. This cylinder might be used on a reciprocating grinder table, where the forces and speeds required in both directions are the same. Various mountings and other options are available on double-acting cylinders, such as rod wipers, air vents, cushions, stop tubes, and a variety of piston rings and rod seals. Rod wipers remove dirt accumulations on the rod to prevent it from contaminating the rod seal and bushing. Air vents allow you to bleed air out of the cylinder to prevent erratic operation. Cushions are devices built into one or both ends of the cylinder to reduce its speed as it enters the last inch or so of its travel. Stop tubes are used where long strokes and side loading may cause wear of the rod bushing. They're placed on the cylinder rod next to the piston to increase the minimum distance from the piston to the rod bushing. Before we leave cylinders, let's take a look at some very basic applications. This shows a simple clamp circuit where the force of the cylinder is holding a piece securely while some work is being performed on it. And in this example, the force of the same cylinder pushes a log through a wedge to split it for firewood. When an application such as a conveyor drive chemical mixer or injection molder requires a rotating motion, a wide selection of hydraulic motors is available. Here in graphical representation we see two types of motors, one fixed and one variable displacement. The fixed displacement motor is depicted in graphic form by a circle and energy triangles, which make it look similar to the pump. In the variable displacement motor, an arrow across the circle indicates that the displacement of this unit can be varied, giving us a change in speed and torque capability. Now then, let's analyze terminology for a moment. In dealing with linear motion, we talked in terms of so many pounds of force required for a cylinder to move a load. With rotary motion, we talk in terms of torque. The definition of torque is simply force times the radius arm. Torque ratings of hydraulic motors, whether they be vane, gear, or piston, are usually given in so many pound-inches of torque per 100 psi of operating pressure. With very large motors, it's usually expressed in pound-feet of torque. Here we have an illustration of a gear-type motor. Oil comes in the bottom port and pushes on the gear teeth, giving us a torque and rotation. If we look closely, we can see this gear tooth, this one, and this one have the same pressure on both sides. Therefore, the forces developed on each side of that tooth are canceled out, and they produce no torque or rotation. Actually, the two teeth at the bottom are the only ones trying to drive the motor. Segments of the two meshing teeth tend to oppose them. So we have the effective area of approximately just one tooth providing the torque. The speed of a motor is determined by its displacement and the flow rate of the fluid driving it. Small motors with a given flow rate operate at higher speeds than large motors with the same flow rate. To reverse a motor, we simply direct the pump flow into the opposite port. Now then, the construction of vane motors and vane pumps is quite similar except for one important fact. In a motor, we must have some means to hold the vane out against the cam rings. Here, we have an illustration of a very basic vane motor. We show a rotor with a single vane being held against the ring by a spring. In operation, the spring would be assisted by inlet oil pressure directed underneath the vane. If this vane weren't held out by some force to begin with, oil entering would just scoot from one side to the other, and no torque or rotation would develop. Here we have a balanced vane motor, very similar in construction to a balanced vane pump. Hydraulic loads developed on this side are canceled out by hydraulic loads developed on this side. Again, the big exception between the construction of a vane motor and a vane pump is the fact that the motor has to have some means, springs, oil under pressure, or both, to hold this vane out against the cam ring. We show this as the inlet side with oil coming in here to give us a torque in this direction. Flow directed to the top port and coming in here as well as in here would give us torque in the opposite direction. Here we have a view of the rocker arm method of holding the vane out against the cam ring. The rocker arm, a special rotor with a pin and clip fastened to it, holds this vane out here and another one here. With two vanes 90 degrees apart, when one vane is moving out of its slot, the other one is moving in, giving us a rocking action which minimizes the flexing of the spring, increasing its life. This is another view of the rocker arm motor. It has a spring-loaded pressure plate. Oil, under pressure, coming in at the bottom port through a shuttle valve in the pressure plate allows us to pressurize the plate. This gives us the force we need to close up the running clearances. That same pressurized oil is also fed through holes in the pressure plate to the bottom of the vanes to help the rocker arm spring hold the vanes out. Because of the reversibility of a motor, leakage oil that collects in the shaft chamber has to be drained externally. We cannot drain the unit internally because at one time or another each port is pressurized. Now, here is an illustration of a high-performance balanced vane motor. It operates at higher speeds and pressures. Like our intravane pump, it features a pre-assembled, pre-tested cartridge for speedy field replacement. We can see that high-pressure oil coming in at this port is directed to the top and bottom of the vane. On the discharge side, we see low pressure top and bottom. Thus, we're balancing out the pressures, top and bottom of the vanes, to reduce vane tip loading. External draining in this unit is accomplished through a port in the cover. Just as with a vane-type pump, if we want to change motor displacement in a given frame size, all we do is simply change the cam ring to one that is wider, larger, or smaller in diameter. Let's switch over now to a study of piston motors. Because of their construction, piston-type motors will usually allow us to operate at higher pressures and speeds than comparable vane or gear units. Here's a simple view of the inside of an inline piston motor. Oil directed into this port gives a force in this direction. Part of that resultant force produces a torque for rotation. The angle of displacement determines the stroke of the pistons and the torque and speed capabilities. A large angle and long stroke gives us high torque and low speed. By going to a smaller angle, we develop a lower torque but a higher speed. If we have a fixed displacement unit, we could have constant torque with variable speed, the speed depending on flow rate from the pump. Here, we have a more detailed view of a fixed displacement inline piston motor. The angle necessary to give us torque and rotation is determined by the angle of the swash plate in the housing and cannot be changed. Most piston units, including this one, must have the housing filled with oil before running. An external drain line is connected from the top of the housing back to the reservoir. A variable displacement motor of this type would have the swash plate mounted in a movable yoke, which could be tilted to different angles during operation. Next, we have an illustration of a bent axis piston motor. It's called bent axis because the center line of the cylinder block is bent off at an angle to the center line of the drive shaft. Some units of this type can operate up to pressures of 5,000 psi. Last but not least, we have the radial piston motor. Radial motors, while not as common as those previously mentioned, are found in applications where low speed and high torque are needed. This type, which is often used in applications such as an injection molding machine, has a maximum speed rating of 100 RPM and a maximum torque rating of up to 16,000 pound-feet. The capabilities of this type of motor often eliminate the need for a gearbox. As you've no doubt concluded by now, hydraulic actuators perform the opposite function of hydraulic pumps in that they convert hydraulic energy back to mechanical energy to perform useful work. In a typical system, the actuator is mechanically linked to the workload and is activated by fluid from the pump, so that thrust or torque is transferred to the work. Okay, that covers actuators, the business end of a hydraulic circuit. And thus completes the third program in our video training series. Again, thanks for your interest in hydraulics. I'm Paul Cook for Vickers.